Hello everyone. Today I wanted to talk briefly about how you can make a custom model for RLlib. Up until now, we've been using flattened observations, and so that is our observation space has been a single flat array of size 5 times 2 times 5, so size 50. But there are many cases when we might not want to just pass in a single flat array. Maybe we're using vision, maybe we're using an image rather than this flat array. So maybe our image is, let's say, 100 by 100 by 3, because we have the width and height of our image are 100, and the number of channels that we have are 3, one for red, green, and blue. Or maybe there's other reasons why we might want something that's two-dimensional with a third channel dimension. So I'm going to show you how to do that. First of all, we're going to go ahead and just import some things for us. So let's go ahead and we're going to import some PyTorch libraries, because we're going to use those to define our model. So I'm going to import Torch. I'm also going to import the neural network module, and I'm also going to import and then the functional model. Just these will help us build our network out, and then also some other RLlib stuff. We're also going to import from array.rllib.models import the model catalog, and also we're also going to import the PyTorch base model class. Cool. So now that we have those imported, first of all, we're going to register our model. And so if we come down to the bottom of our class here, before we initialize Ray, we're going to register our new model with the model catalog. I know we haven't actually defined it yet, but you can make up any string identifier for it. So I'm just going to call it my model, and then also the name of your class. So we haven't defined this yet, or we haven't defined the class yet, but I'm going to call it my model again. And then what we're going to do is we're going to come down here, and we're going to add a little bit to this config. We're going to define a model, and that in that model we're going to define which model we're using, which is the model that we just registered up here, my model. So my model, and then custom model config. Any arguments you want to pass into your model. And in my case, I'm not going to pass in any arguments. I'm just going to define it all in the actual model class, just because we're trying to make this simple here. So again, we've registered our model, and we've added it to our config. So now we can we can talk about our observation space a little bit. So right now, like I said, our observation is being passed in as our observation is being passed in as a flat array. However, we're not going to use an image, but we could pass in this this array instead of passing in the all of the lava and diamond positions separately. We might want to preserve some spatial information and pass in, as it were, an image that's just 5 by 5 with 2 different channels, one channel for lava and one channel for diamonds. And so we're going to use this image shape now, which is 2 by 5 by 5 instead of just an array of size 50. Now we have an array of size 2 by 5 by 5. And the reason you might want to do this is because now we can take advantage of the spatial information, whether there's a diamond or lava, let's say up, down, left, or right of another block. Whereas before we were looking at them all independently and separately. So the agent was not aware at all. If it saw a diamond in one place and saw a diamond in another place, it had no idea if those two places were next to each other or on opposite sides from each other or whatever. Now we could actually learn to take advantage of that spatial information. Coming down to our get observation function, if we scroll down here, we have to change this a little bit too. So that initial array, again, we're going to change the shape a little bit. We're going to say it's 2 by 5 by 5. And I'm going to make a couple other adjustments here, which will be very different depending on what you're trying to do. But basically, in order to still take advantage of this functionality here where we're looping through, I'm going to flatten this. The flatten method will just take this 2 by 5 by 5 and flatten it out to size 50. And I'm doing that just so that I can iterate through the diamond and lava, because our observation floor all comes in flat as an array size 50 as well. But then I'm going to go ahead and reshape it again. So I'm going to use the reshape to reshape it to 2 by, I'm just going to copy this. The same thing it was before. Oh, actually, I have it right here. I'm just going to delete that. Cool. So I'm flattening it, and then I'm putting it back, and then back here where I was flattening it, I'm going to get rid of that. So those are the changes that I need to make here. It's basically just making sure that the observation that's coming out here is no longer flat. Now it's an observation that's the correct shape, which is 2 by 5 by 5. Okay, now the fun part. Now we're going to go up and we're going to define our that my model that we called down here. So it's going to inherit from 2 different base classes actually. One is this torch model v2 that we mentioned before, and another is the nn.module, which is just a PyTorch module. So let's see. Yep. So we're inheriting from both of those. Let's go ahead and define our constructor. The important parts of this. So it is expecting us to pass in just like arbitrary arguments. We're not passing in anything, but it's good to give it the option. So keyword args and args, and we have to call our parent classes. Sorry, some of this is just stuff that we got to do. I don't feel like typing. And module. Okay, nothing passing that. This. Okay, cool. So now we have to define our layers. So the way that PyTorch modules work is we define the different layers in the constructor, and then we have a separate forward function where we define how we use those layers. So usually the forward function would just take in our input. However, because we're making this a torch model v2 from RLlib, they have a few different arguments as well. So their input is actually, instead of just the observation, it's actually a dictionary, and the observation is one of the things in the dictionary. And then it passes in a state and sequence length. And this is just in case you're dealing with like variable length input or recurrent models. We're not, and so we're just going to completely ignore these. And then what we end up returning will be the we're going to return the policy that we get, and then also we're just going to pass the state through because that's what it requires us to do. Okay, one other function that we need to define, and this is not the case for all Torch modules, but it is the case because we're making this for an RLlib PPO module. We have to define a value function, and it just returns a member that we're going to call value. So we're going to set value in this forward function, and then what RLlib does, RLlib will then call this after calling forward to get the value. And it does it this way just because not all of the reinforcement learning algorithms require a value, and so rather than have the value be returned by the forward function, they grab it using a different function. So that's just an RLlib thing. Okay, cool. Now the fun part, we get to define our layers for our model. So I'm going to define several convolutional layers. So this is my first convolutional layer. I'm not going to explain like what these layers all mean in this video. If you want to know more about that, you can Google convolutional layer tutorial or convolutional network tutorial or something like that. I will explain what these different parameters are, but I'm kind of assuming that you already know a little bit. So we have two different channels coming in, one channel for the lava and one for the diamonds. And we get that from the fact that our first dimension in our observation is 2. So it has 2 channels coming in, and then I'm going to specify like an arbitrary number for the out channels. So I'm going to say that I want 32 kind of like hidden channels that to represent my information, my intermediate information. And then I'm going to define a kernel size of 3 and a padding of 1. And I'm going to do this so that I can, it basically by setting the kernel size to 3 and the padding to 1, it will make it so that my height and width of my image stays the same from layer to layer. So if my input size here is going to be 2 by 5 by 5, then my output size is going to be 32 by 5 by 5. And the 5 by 5 stays the same because of these settings. So I'm actually going to define 3 of these. Let's say we have 3 convolutional layers to our network, and but they all have the same parameters, except that now the input to this one will be 32 and 32 because so the output channels here feed into the input channels here, and the output channels here feed into the input channels here. So that's why those numbers are the way they are. Finally, we're going to have two more final layers depending on basically what the neural network for PPO is expecting is it expects a probability distribution over actions for the policy, and it also expects a single scalar value that's the value estimate for that state. And so it's okay if not all of that makes sense. If you have questions, feel free to ask me in office hours. So defining a linear layer, the input to this linear layer, the input dimension, the input size, will be the output, the flattened output of this one. So up until now, this has been a size, let me just define this really quick. So the size here coming, going out of this is going to be 32 by 5 by 5, and that'll be the same for all 3 of these. Now coming into here, we now are going to flatten this out and put it through this linear layer. And so the input is going to be, the input size is going to be 32 times 5 times 5. And then the output we want to be the size of our actions. And so I'm just going to say I'm doing this for the discrete actions, which is 4. So 4 different actions. There you go. Now we're going to do the same thing for our value layer. And it's going to be the same as this one, and you'll see why in a moment, except that our final output is going to be size 1. So don't worry too much about this. I'll explain it all more brief or in a moment. And then, like I said, we have to keep track of this value because it calls it down here. Okay, so now how do we use all of this? Well, we're going to get to our state or our observation from that input dictionary. So let's take the input dictionary and let's grab the observation. This is what it's stored at the key ops. And then what we're going to do next is we're going to go through all of our different convolutional layers. One thing that's important for a neural network is that you have non-linearities between your layers. And so we're going to use the non-linearity function RLu. So I inputted functional before, so I can do f.RLu. And then the convolutional layer will feed directly into that. So what I'm doing here is I'm taking that observation, passing it into the convolutional layer, and then passing the output of that into the RLu nonlinearity function, and then getting the output. And we're going to do the same thing for all 3 of our convolutional layers. So nothing fancy there. Finally, or next, we're going to flatten the output of this last layer, because linear layers have to have flat inputs, whereas the convolutional layers have 2-dimensional inputs, or 3-dimensional, I guess, because of your channel dimension. So I'm going to flatten this. However, I'm not going to flatten it all the way because these convolutional layers, they are not exactly this size. So let's define our sizes here just to make this easy. So the input size is 2 by 5 by 5, but it's not actually 2 by 5 by 5. There is an extra dimension at the beginning because it will actually pass through batches of this at a time. A batch is basically just saying, I want to send through a bunch of different examples through my neural network at once, and so we call that a batch. And so maybe your batch is 10, maybe your batch is 1, maybe your batch is 100. We don't care, but there's a batch dimension here. There's a batch dimension in front of each of these, but this is going to be the output of this layer. So here x is equal to, or the dimensions of x is equal to batch by 2 by 5 by 5, and then it's batch by 32 by 5 by 5 all the way here. And then when we flatten it, we don't want to flatten the batch dimension. We want to leave that here. We just want to flatten these last ones to a size of 800. And so the way we do that is by doing dot flatten start dim equals 1. Basically, that's saying it'll flatten starting at the first dimension, so starting here. That'll give us this shape. And then now that we have this flattened array, linear layers do handle batch dimensions, and so linear layers can handle 1 or 2 dimensional input if the first dimension is the batch dimension. So then we're going to have our policy is going to come out of the self.policy layer, and the value is going to come out of the self.value layer. Okay, cool. The output of this then is going to be batch by 4 because our action space is 4. And the output of this then is going to be batch by 1 because we just have a single value for each of those states. Last thing, actually, this value function, before I forget, doesn't expect us to return batch by 1. Notice that because this dimension is 1 here, we can actually just get rid of it, because basically what this is saying is we have like a 2-dimensional array or a matrix, but the column size is 1. And so it just wants, we can, instead of returning matrix, we could just return just an array here, so just 1-dimensional, and we can do that by squeezing. There's a function called squeezing the first dimension out. And so whereas it was batch by 1, we're going to squeeze that dimension here and just return an array. Cool. So this is now our neural network. To review, our observation comes in with a size of 2 by 5 by 5, then goes through 3 different convolutional layers. The output of each is 32 by 5 by 5 because of the settings we specified here. Then that goes and is flattened, and then is passed into a policy and value layers, and we return the policy in the forward function, and the value is grabbed out of the value function. And now we should just be able to train our same diamond collector, but with this new neural network here, rather than our the default neural network. What it was using before just had linear layers, just so you know. So it was just using linear layers, and that's the default network. If you want to use convolutional layers, then you'll want to define it yourself like this. Or if you want to use linear layers, but you want to have more control over exactly what's going on, you can define your own model here. So that's how you do a custom model. And just to show that it works, or to show that I can't live code and that I'm going to have bugs, we can play this here. Oh, I didn't even save. This is the wrong one. This is so exciting. We'll see if I actually did this right. Then it should be able to train. And if you have any questions, you can always reference the docs. So while this is getting started, I'll show you the docs. Basically, here in the RLlib docs, if you come down here to customization, it links to the neural network models customization. Basically, you can customize the different parts of RLlib. If you want to customize your neural network, then you can do so. It describes how to do that here. And if you scroll way down, I guess I could just, if you scroll way down to custom PyTorch models, then it defines this torch model v2 and gives you some documentation for how to do it, and even an example here at the end. It's not quite fleshed out, like it doesn't actually define the different functions, but you can use mine as an example. It's kind of a starting point. Anyway, hopefully that's helpful. And look at that, I did have a bug. Let's see if I can debug that really quick. Okay, all's well. We're working now. I saw a little typo in my keys down here, but yeah, so I will post this file to CampusWire, and post this video just in case it's helpful for any of you on your final projects. Good luck.